Jai Hind everyone, myself Ankita, Faculty of Department of IT, AKGEC. Today I am going to discuss the topic Constraint Satisfaction Problem, that's part of Unit 2 of course BCS 0701. Now in this I will be discussing the introduction to CSP, I will discuss examples of CSP and how can we formulate a CSP problem, constraint graph, and finally cryptarithmetic problems. Now till now whatever we have discussed now, like your informed search techniques or uninformed search techniques, local search techniques or adversarial search techniques. In all of these search techniques, we were searching in the spaces of states. So we have various states, and when one of these state was a goal state, and we were searching for that goal state among your state space. So in the previous techniques, we were searching in the spaces of states. Now, these states can be evaluated via domain-specific heuristic. So, depending upon the type of search technique that we are using, we use the heuristics and we will check whether the state that we have reached is a goal or not. So, in the states or in the spaces of states, we were searching for a state, and each of these state was atomic or indivisible. So, we were not considering we were considering each state as a black box, and we were just trying to find out our goal state amongst all the possible states that were present in my search space. So in contrast to that, CSP does not consider a state to be a black box. Instead, it considered a factored representation of a state. So it considers that we have a state and it has certain variables that defines a state. Okay, so instead of considering a state as a black box, in a CSP, constraint satisfaction problems, we considered the factored representation of a state, wherein a state consists of a set of variables, and our task is to assign the values to these variables provided some constraints are met. Okay, so a problem is solved when each of the variable has a value that satisfies all the constraints on the variable. So in your constraint satisfaction problems, we have a state, okay, and that state is represented as a form of some variables, and our task, or we can say the goal state, would be when we are able to assign values to these variables in sync to the constraints that were defined. So when we try to define a constraint satisfaction problem, so before going to that, it's very simple example of a CSP problem is a Sudoku problem. Now in a Sudoku problems, we have certain numbers that we need, certain spaces where we need to assign the numbers, right, to the blank states, right. So our task is to assign all the values to the blank states till we get all the constraints satisfied. Okay. So a constraint satisfaction problem, it consists of three components. Okay, first is a set of variables. There are variables. What are these variables? These are the variables for which we have to find out the values for. Then what are domains? Domains is that these variables can get the value from these domain values. So DI consists of allowable values for these variables xi. And then we have a constraints that specifies allowable combination of these values. So constraints is what set domains is all possible values that can be put to the variables, and constraint specifies what is the allowable combinations from the domain which can be put into variables. So each constraint consists of a pair called as scope and rel, whereas scope is a tuple that participate in the constraint, whereas rel is the relationship between the variables. So when we talk about a Sudoku problem, suppose I have a Sudoku like this. So it is some sort of Sudoku. So I have some these values. Okay. Now my task is to assign these values to these blank spaces, considering what are the domain. Domain will be any number could between 0 to 9. Any digit that between 0 to 9 I can put on these blank spaces, whereas my constraint could be that the length of these, in the row I cannot put values beyond 5, right. So this is a constraint that we need to take care of. So when we are assigning the values, how should we assign the values? Now we have a variables xi and xj represent the variables, whereas vy and vj represents the values. So an assignment does not violate any constraint, then we call it as a consistent or legal assignment. So if we are able to assign values to the variables according to the constraint, we will call it as a legal assignment or consistent assignment. So when I'm able to assign every variable in my state a value, a consistent value, we can call it as a complete assignment. So a solution is to a CSP is consistent complete assignment. So what is the solution to my CSP problem? When I'm able to assign the values to all the variables in my state in accordance to the constraint, then we can say that is the solution to my CSP problem. So when I am doing the complete assignment, I can reach to the solution. If there is a partial assignment, that is we can assign only few variables to the some values, consistent values, we call it as partial assignment. Now examples of CSP is very simple example is your Sudoku problem that we have always do play in our lives. So in Sudoku problem, the variables are empty cells. So we have to assign values to these empty cells. And what are the domain? Domain is any value between 0 to 9. 1 to 9 I can assign values, right? That is my domain. And what is the constraint? Constraint is says that no number is repeated in a row, column or 3 by 3 subgrid. So these are the constraints. So every CSP problem is depicted by three things. First is your variable, that is the empty cells. Second is the domain. What are the possible values that could be put to the variable? So in case of Sudoku, my domain is 1 to 9. And third is your constraint, right? Constraint says what values I can put for. The constraint is there should be no repeated values in a row, right? In a column or in a subgrid. So that is your Sudoku puzzle, okay? Another example is scheduling problem. So whenever we want to find out the timetable or so we have the constraint. So in a course scheduling means we are finding out the timetable. So variables could be the slots in a timetable, domain could be the various subjects, and constraint is that any faculty that is teaching one subject, okay, cannot teach the another subject in the same time in different class. So that is my scheduling problems. Then map coloring. So map coloring is there when we have a map of different countries and we have to ensure that no two adjacent countries will have the same color. So this is a map coloring example that we usually use to explain CSP problems. So these are the various examples of your CSP, that is Sudoku, scheduling and map coloring. Now how can we formulate a CSP, that how we can represent a CSP? So variables, this is a map coloring example. We have the various parts of Australia, Western Australia, Northern Territory, South Australia, Queensland, New South Wales and Victoria, Tasmania. And these are I have to assign colors to these countries so as to they are not, adjacent country does not have the same color, right? So variables x is equal to, x will consist of all the variables that I want to put value in, right? So it will Western Australia, Northern Territory, Queensland. So this is my variables. Domains are the color that I want to put in. So here the color that I want to put in is red, green and blue, right? And what is the constraint? Constraint is adjacent region must not have the same color. For example, the Western Australia and Northern Territory cannot have the same color, okay? So that is how we formulate or depict a CSP problem. Next is when we can say the solutions are complete and consistent. It can be complete and consistent when we have the full solution, right? So we are able to assign color to each of these territories, and also I am able to pick the values from my domain, right? And third, any of the constraints are not missed, okay? Now, whenever we're trying to solve a CSP problem, we try to make a graph of it, okay? For that, we are making a constraint graph. So, constraint graph, the nodes are the variables that we want the values in, and arcs show the constraint. So, whenever we have a binary CSP, it means we have a constraint that is related to two variables. So, we can always convert a non-binary CSP to a binary CSP. For example, now this is my territory and I have to put in colors to it. How can I depict it in the form of constraint graph? That for each of these variables are depicted as nodes, and since the color of Western Australia and Northern Territory cannot be same, so I have put a line note to it. Color of Western Australia and South Australia cannot be same, so I have put a line to it. So all the constraints are depicted as the arcs, whereas the variables are depicted as the nodes. So this is how we are making a constraint graph so as to make the solve the CSP problem. Next is, what are the different types of variables? So there are two types of variables. First is discrete variables and continuous variables. Now what are these variables? These are the variables of a CSP problem for which I want to put a value in. So discrete variables will have only discrete values, that is from 0, 1, 2, 3 like that. So if it is finite domain, okay, so we can call it as finite domain CSP, and if the domain is infinite, for example, I am telling that it could be any integer, then it is infinite domain. So finite domain CSPs are obviously, but they have limited number of possible values for each of these variables, and these problem space is managed but can grow exponentially as the number of variables increases. So if the number of variables increases, it becomes more difficult to solve the problem, right? For example, if I have n variable and the domain size is d, so my possible assignment will be order of 10 raised to the power n. For example, if any variable can take 3 values, okay, the domain is from 3 values and we have 5 variables, so there will be 243 possible assignments and I have to choose the best or correct assignment. So that was my finite domain. And for the infinite domain, the domain could be anything, any integer values. For example, string or integer. For example, job scheduling, right? Example is your job scheduling. Next is the continuous variables, when the variable can take any real value. So it could be infinite range, right? So continuous range, for example, scheduling task in Hubble telescope observation that starts and end time might represent a continuous variable because time can be infinitely subdivided into smaller parts. So these are the various types of variables that we have in your CSP, that is discrete variables as well as continuous variable. In discrete variables, we have finite domain in which the domain of my CSP is limited, whereas infinite domains can have any integer values. In continuous variables, we can have any real numbers. Okay. Now also likewise we have type of variables, we have type of constraint. It could be unary constraint, binary constraint as well as higher order constraints. Now in unary constraint, it involves only single variable. Binary constraint involves a pair of variable, and higher order constraint involve more than 3 variables. So unary constraint says the South America cannot be green. Okay, binary constraint will have the color of these two states won't be same, whereas higher order constraint example is your cryptarithmetic problems that we will discuss later on. Now, what are soft constraint? Now, soft constraint is preference. So, red is better than green. It is not strictly that we want it, but it is, more advisable to have it. So, that is your soft constraints. That can be violated, but it is not preferred to be violated. Okay. Now, how we solve a cryptarithmetic problem? First example that I have taken is node coloring. Now, in node coloring, I have got 4 nodes, and this is my number of variables that I want to assign value to, and these are my domains. Okay. Now, this is my constraint that adjacent nodes should not be of same color. So, initially, I have put the table like this, 1, 2, 3, 4. Initially, any of these 3 colors can be put to any of these 4 nodes, right? Suppose that I put one node as red. Okay. Now, my one node is red. Now, when my one node is red, now 2 cannot be red because 2 adjacent nodes cannot be red. So, 2 cannot be red. So, I have removed this from all of these 2, 3 and 4 because 1 is connected to all of these nodes. So, here I have got this. Okay. Now, in second iteration, I have chosen green for second. Okay. Now, when this is my red, this is my green. Okay. Now, see, 4 cannot be green. So, it has to be removed. 3 could be green because these are not adjacent. This is a constraint graph. Okay. So, now I reach to this state. Now, suppose that for third, I put blue. Okay. Now, when I put blue to here, I could find out that 4 can neither be red nor be green, or it cannot be blue also. So this will be my error condition. So what I will do, I will backtrack and I will give, instead of B, I will give 3 as green color, because it can be anything by G or B, right? Green or B. So in 4, I will ultimately have my B color. Okay. So this is my node coloring example to solve a cryptarithmetic problem. Now, cryptarithmetic problems are the type of CSP problems in which we have an alphabet which is associated with a unique digit. Okay. Examples are 2 plus go is equal to out, sum plus more is equal to money. So these are the various cryptarithmetic problems. And the domain is, we can put the values of these alphabets as 0 and 9. And what are the constraints? Constraints are, each alphabet or a variable has a unique digit. The digits cannot be repeated. The range is from 0 to 9 and only one carry should be found, and it can be solved both sides, and some of the digits must be as shown in the problem. So these are the constraints that we need to require to solve your cryptarithmetic problem. Now, for example, I have to prove 2 plus go is equal to out. Okay. Now, the constraints are, I have to assign these alphabet a numeric value ranging from 0 to 9. Okay. Another constraint is that the values cannot be repeated. For example, if these have value 2, I cannot assign 2 to any other alphabet same value, right? And third constraint is that they should be able to, we are able to, plus the values. For example, value of O plus O should be equal to T. Okay. So let's start solving it. TO plus GO is equal to out. Now, since this is the rightmost digit, okay, sorry, leftmost digit, okay. Now, this digit should be 1. Why it should be 1? Because we don't have any digit over here. So it means it is a generated carry. So generated carry could maximum be 1. So O is equal to 1. Now when O is equal to 1, so here also I have 1 and 1. So T is equal to 2. Okay. So I have got two numbers. O is equal to 1 and T is equal to 2. Now 1 plus 1 is equal to 2. I will put the values over here. Now you can see 2 plus G is equal to U plus 10. Why? Because here this is the value of carry. It means this number is, the sum of these two numbers is generating a carry. So it could be U plus 10. So here we have to put an assumption that to generate a carry, either G should be 9 or 10, right? If it is 7, and 7 plus 2 is 9, so there will be no carry. So we have to generate a carry. So therefore, the value of G could be 8 or 9. Now, when I put G is equal to 9, suppose G is equal to 9, so it will be, U will be equal to 1. Why? 2 plus 9 is equal to 10. Okay. Now, here the 10, yani ki U is equal to 0. This is not possible, right? So, therefore, we put the value of G is equal to 8. Okay. Now, when G is equal to 8, it will be 11. So, U is equal to 1. It's not possible 1, right? So, this is not possible 1, and therefore, we have put a value G is equal to 8 and yet I U is equal to 0. So, after putting or solving all this, I reach to this solution. Now, next problem is send plus more is equal to money. How should we solve this? Now, see, this is my extreme left. This is also a result of a carry. So, M is equal to 1. Now, here I have assuming that S is equal to 9 because we have to generate a carry. Okay. So, 9 and this is 1 and this is 1. So, what will happen? O will be equal to 10. Okay. The O value will be 0. So, I have found out three values. S is equal to 9, M is equal to 1 and O is equal to 0. Now, this is my 9. This is now you can see we are knowing that S is equal to 9, M is equal to 1, O is equal to 0. Now, E plus O is equal to E. Okay. Now, see, Since it is 0, the value of O is equal to 0, it means it is there is a carry generated over here. Okay, so I have written 1 over here. Okay, so 1 plus E plus 0 is equal to N. Fine. Also, N plus R. Now here I am not sure whether the carry is generated or not. So I have just put that in a bracket, is equal to E plus 10. So this is for the carry generation. Now when I put the values of N in this equation, I will get N plus R plus 1 is equal to N की value हमने यहाँ से डाली, N is equal to N E की value. We have put the value of E from here. Okay, so E is equal to N minus 1, N minus 1 plus 10. So I get R plus 1 is equal to 9. So I'm not sure whether there is a carry generated over here or not. I'm not sure of it. So I will just try and check. So if there is no carry generated, suppose there are two conditions whether the carry is generated or not. If the carry is not generated, means the value of R is equal to, R is 9, but R cannot be 9. Why? Because we have already assumed the value of S to be 9. So it means R could not be 9. So therefore the value of R is equal to 8. It means the carry is generated. Now I have got same 1, 1 and the carry is generated. Now again I will put the values. Now you can see D plus E is equal to, should be greater than or equal to 11. Why? Because Y cannot be 0 or 1. Why cannot be 0 or 1? Because we already have 0 and 1 in our assignment. So Y cannot be 0 or 1. Okay, so it should be greater than 11. So we assume that Y is equal to 2. Now when we assume Y is equal to 2, it means D plus E is equal to 12. So D cannot be 8 or 9. Why? Because it has already been assigned. So we assume the value of D to be 7, and automatically if value of Y is equal to 2, so the value of E will be 5. Now when D is equal to 7 and E is equal to 5, we reach to this stage. Now after solving, I can find out and the value of N is equal to 6. So this is how we are going to solve a cryptarithmetic problem. Now whenever we are trying to solve a problem, this is how we solve it. But when we try to solve a CSP problem through a machine, we have to formulate it as a search problem. So my initial state will be the all variables are unassigned, and what will be my successor function? A value is assigned to one of the unassigned variables which have no conflict. So my purpose of the successor function is to find out the assignment so that no constraints has been violated. So that is my successor function. Now goal test will be when we have complete assignment. All the constraints are satisfied as well as all the variables are being given values. And what is the path cost? A constant cost for each step. So solution will appear at depth n if there are n variables. So here we can formulate a CSP as a search problem and we can solve it. So like here, my successor, this will be my initial state where I have to assign values to these variables. Next step is to find out the successor function. Like that we were assuming how we should assign the values so that there is no conflict in the constraint violation. Okay. And then my goal test will be whether all the variables have been assigned the values or not. And the path cost will be the constant cost for each of these steps. So this is how we formulate a CSP as a search problem. So that's it for now.